Okay, so the first one, both EM waves and sound waves, so that's transverse and longitudinal, can be reflected. State two other wave phenomena that apply to both EM waves and sound waves. So both these types of waves can be diffracted and refracted. Okay, so explain why EM waves can be polarized but sound waves cannot be polarized. Well, polarized can only occur with transverse waves, so sound waves are longitudinal. So it can't be polarized. So describe briefly an experiment to demonstrate polarization of microwaves in the laboratory. So microwaves have a transmitter and they have a receiver. And they are emitted and received by a receiver, and on the receiver there is there's an analog scale, and pointer. When you get a maximum signal, the pointer will go up, and then when you get a minimum signal it goes back down to 0. So looking at the mark scheme, you've got 4 marks. So I'm going to say that the transmitter and receiver are on the same plane or on a bench facing each other. So T and R are facing So the second thing I'm going to do is use a filter in between, and the filter looks like a metal grid. So place a metal grid so waves emitted from T are in all planes. So waves emitted from filter number 1 are plane polarized. So then I'm going to take another filter, I'm going to rotate this filter by 90 degrees. So I have the metal grid lines at 90 degrees. Rotate second filter. Through 90 degrees. My signal drops from a maximum to minimum. Don't say that it drops to 0, because sometimes you do get a little bit of a signal through. Just say the signal goes from a maximum to a minimum at 90 degrees. If you were to rotate this grid again back through another 90 degrees, so it's 180 degrees from where it started, then you would get the signal would go back to a maximum again. So this is a sound wave emitted by a loudspeaker, single frequency, so displacement. I'm checking out that the units are millimeters and this one's milliseconds. So whenever I say a milli, it's times 10 to the minus 3. And this is times 10 to the minus 3, and I'll write it underneath so I don't forget when I come to do my calculations. So I need the amplitude, so the amplitude is the maximum displacement from equilibrium, which is 0.3. Don't forget this, times 10 to minus 3 meters. Well, it's asking for millimeters, so it's back to 0.3. The frequency of the sound wave, or frequency, how many waves in 1 second, which is 1 over the time period. The time period here is the time taken for one complete wave. Is 1 divided by 4.0 times 10 to minus 3, and that will equal 250 Hertz. You'll get 1 mark for that and 1 for that. Okay, the sound generator is adjusted so the loudspeaker emits a sound at original frequency, so the same type of sound and twice the intensity. So sketch on the new displacement against time graph at point P and explain the reasoning. So we have to realise that intensity is proportional to amplitude squared. So 2 times the intensity is proportional to 2 times amplitude squared. So we square root both sides. Root 2 times square root of the intensity is proportional root 2 times the amplitude. So the amplitude is increased by a factor of root 2. Root 2 equals 1.41. So 0.3 times 1.41 so 0.3 times square root 2 equals 0.42. So my new intensity will have an increased amplitude but the same frequency. So I'll mark on my graph roughly 0.42. create the same sine wave but with increased amplitude, making sure that I go through all the points very, very carefully. So I can bring it back here. So I can bring it back to here. Should look something like that. Okay, so just with the reasons, the apparatus you would choose to detect and measure the frequency of the sound at P. Okay, so I need to detect and measure frequency. So detect a sound wave. There's a microphone. And measure, I need an oscilloscope. So the microphone is to transfer mechanical motion to electrical signal, and this one is to display oscillations over time, over a time period, to measure frequency.